Uh-oh. Okay, so let's start easy here. What do we do with something like this? Okay, good. If we have a square root of a fraction, let's kind of think about, it's been a while. Let's get back, think strategically on this. First of all, can we reduce the fraction? No. 1/25 is reduced. So then we split it into separate square roots, top and bottom. What about this negative out front?
That's going to go with both of them.
Yeah, that's an outside. What is that outside number?
So 1.
Well,
-1.
-1, right? So we have an outside number of -1. It's already outside. It stays there. Don't get confused by, like, they're going to throw something at you, a possibility in your answer here that says the root is not a real number, which would happen when? When would you choose option B? Okay, if you're taking an even root, so like a square root and you have a negative number inside, then it's not a real number. Okay, but this is an outside number, so we're okay. It just stays there. And then we're going to break this up into separate square roots, square root of 1 over square root of 25, and those both simplify immediately. What's the square root of 1?
1.
What's the square root of 25? So we got it, right? What's our answer? Well, almost. -1/5. There you go. Yep. -1/5. Okay, give me thumbs. How we doing? All right. Okay, what about one like this? Now, what kind of root is this?
Cube root.
Cube root. Okay, so we've got this negative inside. That's scary. Is that a problem?
No.
It's not a problem. How come a negative in this case inside is okay? Because it's an odd root. Exactly. We can take an odd root of a negative number. An odd root of a negative number gives us an answer that is always what? Negative. Yeah, absolutely. And so what is the answer here? What is the cube root of -27?
3.
-3. And why is that? So we know the answer.
3 times 3 is 8. Or 3 to the, no, 3 like cubed.
Okay, good. Because -3 cubed, here's the reason why. The answer is -3 because -3 cubed is -27, right? Okay, make sense?
Yeah.
All right. Okay, no big deal. This is not so bad, huh? And there's another one that's really, this is light work. What are we doing here? We've been doing this all year. What's that mean? If f of x equals the square root of 2x plus 3, find, how do we say that?
Find, it's like basically x is 3.
Okay, but how do we say that?
Find
F of 3, right, right? Good. It's not, and remember, it's not, we talked about this at the beginning of the year, it's not f times 3 or something crazy like that. It's f of 3. We're just plugging 3 in for our x variable. And what does that give us if we...
That's going to give you 2 times 3 plus 3 inside there. 2 times
And
5.
what is 2 times 3 plus 3?
That'd be 9.
9.
9.
And what's the square root of 9?
3.
Oh, okay.
Okay.
So that's our answer, isn't it? Good? Okay. Okay, so now we've got these rational exponents. Remember, rational means fractional, right? So rational exponent means fractional exponent. So 16 to the 1/2. Now there's two things they want you to do here. First of all, they want you to rewrite this expression using a radical, okay? So what would that look like? What does a 1/2 power mean? Say it again. 16 squared? Oh, okay. Square root. Okay, remember, this is that stuff where whatever's on the bottom of a fractional exponent, that becomes the index of the radical, meaning it tells you what kind of radical you have, right? So we said this. Some number to the 1 over n power is just the nth root of that base, right? Okay, so this would end up being a square root because the index of the radical is 2. Okay, give me thumbs on that, up, down, sideways. Does that make sense? Square root of that number, 16. So there's the first part. They just wanted us to rewrite the expression using a radical instead. Now we haven't simplified this all the way. Well, what do we get if we simplify that all the way? 4. So our final answer, if we simplify it, is just 4. Okay? Everybody see what they're asking for there? So make sure on that when you read that carefully, because what people would be tempted to do is just write 4 there, but that's not what they're asking. Okay, give me 1 to 5 on this one. 5, you guys know the rules, 1 to 5. On the understanding the question, how to answer it. Okay? All right. Questions? How would you know? Like, what about the instructions tells you not to put a 4 here? Okay, do not simplify, exactly. And then the other thing I think is this, using radicals, right? They want you to write it with a radical. Remember that fractional or rational exponents and radicals, they mean the exact same thing. It's just that they're different versions of the same thing, depending on which one you want to use, right? They're equivalent. Okay, now this time, again, we're not trying, well, we can't really give an answer because it's an x, right? We can't simplify this. But they want to convert the expression from exponential form. Everybody see that's, why is that exponential form? Because it's written with an exponent. There you go, yeah. It's written with an exponent, that's a fraction in this case. So we want to go from exponential form to radical form. Okay, so 2 things are going on here this time. We've got a 9 in the denominator of our fraction, which means what kind of root is this going to be? 9th root. And what do we do with the 4 that's in the numerator? That's the regular power of the base. Okay, so we end up with that. Everybody see that? Okay. The 4 stays, that's the power of the base, and the 9 on the bottom tells us the kind of radical we're using. Okay? All right, give me 1 to 5. How we doing? Good? Okay. Okay, so this time they want us to just simplify this. So what we want to do, you don't necessarily even have to write this out, but in your mind you've got to think about this in terms of a radical. So let's do this. First of all, let's just write out what would this look like if I wrote this using radicals instead of fractional exponents. Okay, I've got the square root of 9 cubed, right? Or we have an option here. In that previous example, by the way, we could have written this 2 ways, and they both would have been fine. You could have entered this in the answer box, either of these 2 ways, and it would have been fine. Here we chose to do the power first and then take the root using PEMDAS, right? Because we're starting inside the function. Did everybody get that? We also could have chosen to take the 9th root of x first and then taken it to the 4th power. Either one is fine. Either one is fine. This one's a little easier to write. That's probably what I would choose for this answer. But in this case here, yeah, I mean, that's kind of not a great way to do it, isn't it? Because that's saying the square root of 9 cubed. What's 9 cubed? 729, but not many people are going to remember that probably, right? So that's really not a very convenient way to think about it. Square root of 729, what's that going to be? I mean, that's a big number to take a square root of, right? We'd have to make a factor tree and do all that stuff. So instead, how would we probably want to write this? The square root of 9, so we'll square root first and then cube the result. Isn't that easier? Remember we talked about that? It's when you have a fractional exponent like this, it's always easier to do the root first because that gives you a small number that then you can take to a power and get a bigger number, right? So what is the square root of 9? Cubed? Way easier, right? Okay. So do the bottom part first, and you can even do it in your head. We know that a 1/2 power is a square root, so square root of 9 gives us a 3, which we cube, and we just get 27. Okay? Give me 1 to 5 on that one. Okay? Good. Good, good. All right, what about this? Use the properties of exponents to simplify the expression. Okay, so this, yeah. And then they just want us to write our answer in exponential form with a positive exponent. Okay, this is super easy. We're just using a property of exponents that we've used many, many, many times. If we take our property of exponents was a to the m times a to the n equals what? In other words, if we multiply powers with like bases, what do we do to the exponents? We add them, absolutely. We get a to the sum of the two exponents. Well, do I have like bases here? What's my base? No, what's my base? B, right? The base of the power is the thing that's being taken to a power. So we have like bases, so we're going to get B to what power? If I multiply like bases, you just told me I add the exponents. So what's the exponent going to end up being if I add those? 3/5 plus 6/5 is 9/5. And 9/5 doesn't simplify, so we're stuck. That's our answer. They want the answer using a positive exponent. So that's it. Okay? No big deal. All right, what about something like this? We've already got a 4 outside, but I've got a pretty big inside number, 112. What do we do with these? We want to simplify a square root like that. Remember, our job is to get as much out of the radical as possible. It's been a little while. What's that? What was our saying we used when we're simplifying a square root? What goes out and what stays in? Oh, yeah, couples go out, singles stay in, right? Factor tree, there we go. Okay. So let's factor 112. What's something that divides into 112? 16. Does 16 go into 112? It might. I don't think so, because it goes into 96. Yeah. 2 does. We could do 2, right? Because it's even. We'll just do that. So 2, what's half of 112? 56. So we get 2 times 56. I can circle 2 because it's prime.
16 does go into 112 though.
It does?
16 and 7 make 112.
Oh, okay. Oh,
So
man.
do that instead of
Yeah.
2 and 56.
Okay, yeah, we should have, definitely. Okay, okay. Let's go back. I like that. That was good. You're right. So 7 and 16. Oh, that's way better. 7's prime. And then 16 is a great one. What does that break up into? 4 and 4. So look, I get a couple of 4s. Couples go out, singles stay in. Okay, this is going to be easy then, right? So we already have a 4 outside. Anything else go outside? 4. There you go. I get this. Whoops. I'm going to multiply by another 4 outside. And what's inside? 7. Okay, so is our answer totally simplified? What's the last thing I could do? Yeah, multiply the outside numbers together, right? So we get our final answer then. Just looks like 16 outside and 7 inside. Okay, good? Remember, couples go out, singles stay in. What if we were doing a cube root? What would go out? Triples. And everything smaller would stay in, right? Okay, good. All right, what about one like this?
one, you want to do the same.
So the same thing for the 72, right? For the number part.
You want to do the factor tree, yeah.
Okay, so let's make a factor tree for 72, and this is going to be a pretty easy one.
9 and 8. 9 and 8.
Okay,
I would just
could we even do, 9 and 8 is going to work, but could we even do something, like is there a, we want to see if we can find one of our,
12 and 6.
that would work too. Okay, let's do that, 12 and 6, that's fine. So 12 and 6, how about the 12? What is it? There you go. We could break it into 2 and 6. And now the 6s would break down further, wouldn't they? But do I need to? I don't need to, because look, I have a couple of 6s right there, and there's no reason to break down big couples, because I'm just going to get a bunch of smaller couples that multiply to 6, right? So this part is going to stay outside, go outside, oops, and this part is going to go inside, right? So the number part is done.
I had to do the 13. I don't know to do the 13, bro.
Outside number 6, inside number 3. What did we do about the square root of x to the 13th? Do you remember that? Because that's the other part we got to deal with. How do we deal with the square root of x to the 13th? Okay, it's been a long break, but what did we say about that? We want to write that as, instead of using a radical, we want to write it as what? As what? The exponential form, as a fraction. What would that be? The square root of x to the 13th is the same thing as x to what fractional power? 13 halves, there you go. The 13 stays on top, doesn't it? Because that's the traditional exponent of the base. What goes on bottom is going to be whatever kind of radical we have. It's a square root, so the index is a 2. So we're going to get a 2 on the bottom of our fraction, right? So x to the 13 halves. And then all we had to do from there was take that fractional exponent and turn it into a mixed number, right? And what did we say about that? The integer part, the whole number part of the mixed number is the power of x that goes outside, and the fractional part is the part that's stuck inside, right? So what is 13 halves as a mixed number? 2 goes into 13 how many times? 6 are what? R means remainder, right? With remainder 1. Okay. So this is the same thing as saying x to the 6, oops, 6 and 1 half, right? And that was, we got that just from 6 R 1, right? Everybody agree? So what'd that tell us then? That told us that we got an x to what power outside? 6. And what power did we get inside? The 1, right? Because I have an x to the 1 half. The 2, remember, corresponds to that 2 on the radical. It's a square root. So the denominator of that fraction means square root, and the 1 is the power of x that's inside the radical. Is this ringing a bell? I know, again, it's been a whole week. But when we took that 13 halves, we have the fractional exponent for that variable. When we simplify that, when we write that as a mixed number, you guys told me it was 6R1. The 6 is the outside power of the variable. The remainder is the inside power of the variable. Right? Okay? And so that's our final answer right there.
Why is there a 3 in
Because that came from the 72. Remember when we made a factored tree out of the 72, we got a couple of 6s and a single, oh, it should be a 2. Yeah, there you go. Yep. You're right. You're right.
Yeah, no, man. He needs to come back.
That's what you meant. It should be a 2. Okay. Everybody good? Okay. Okay, give me 1 to 5 on that. Okay, so we need to do one more of those. Okay. All right. Let's do one more. Okay. Yeah.
I said the index in the book, you know what I'm talking about? Like, flip it open. Jules, the other one. Jules, give me a book. I'm gonna know that. So it's
Okay, you guys want to try this one on the board?
Yeah.
Go for it. Try that on the board.
so I'm excited.
Okay, here we go. You got to talk me through this one. So 48, we got to make our tree. What do we get for 48?
6 and 3. 13 and no. Oh my God. 6 and 8.
6 and 8 we could do. Okay. 6 breaks up into.
3 and 2.
Okay. 3 and 2. 8 breaks up into 4 and 2. And what's the 4 going to break into?
2.
So let's cheat. Let's just do that. 8's going to break up into 2 and 2 and 2, isn't it? Everybody agree? Okay. So what do we get then? Well, it looks like we got a couple of 2's and another couple of 2's and a single 3, right? So what's that mean then? What's our outside number going to be? 4. Good, because outside we're getting a 2 and a 2. Good. And what's our inside number? 3. Okay, what about x? Now we have x to what power? 21 over 2. Whoops. And if we look at 21 over 2, what is that? Yeah, okay, 2, that's, if I simplify that ratio and write it as a mixed number, we're going to get 10 R1, so 10 and 1/2, right? So then what's my outside power of x? 10. What's my inside power? Uh-oh, this is going to blow. Okay, but we'll get through a little more today. So what about this one? This is a really easy one. How do we organize this? Chromebooks should be closed. I see some open Chromebooks. Let's get those closed. So what about this one? How do I deal with this? I've got I'm multiplying two numbers that involve radicals, and I've got inside and outside numbers. So what do I do here? I need somebody, new contributor here. What's that? Okay, yeah. I multiply the outside numbers outside, so what's that going to give me for my outside number?
12.
Yeah, there you go. Good, so my outside number becomes a 12, and my inside number is a 15, yeah. Okay, now when we do that, remember that we always have to look at the radical that we end up with and ask ourselves, could we simplify that if we did couples go out, singles stay in? Are there any couples in the factor tree for 15?
No.
No, so that's our answer. We can't, there's no couples to go out, right? Okay, give me thumbs. Good, all right. Okay, what about this one? What's the plan here? Yeah, just distribute, right? We're just going to distribute. And it's just a bunch of the stuff we've already talked about, but there's a lot of it because I have to distribute. So I distribute the 8. What's 8 times 2? 16. 8. Well, what am I going to get there when I distribute? What's my outside number going to be? -8, because I'm multiplying the outside number 8 times the outside number No. What's the outside number there of that second term? Negative 1, yeah. So 8 times negative 1 is negative 8, and then I've got the inside number, square root of 5, right? Good? Okay, what if I distribute this square root of 5? Yeah, I can't combine those because one's an outside number and one's an inside number. So they stay that way, 2 times the square root of 5. And then finally, what about this? Okay, I get negative the square root of 25, but what's the square root of 25? There you go. And then I could combine some like terms here, couldn't I?
Yeah.
What's one pair of like terms?
8 times negative 8 times square root of 5 plus 2 times the square root.
Okay, so now how do we add those up? Let's look at this sum right here. Negative 8 times the square root of 5 plus 2 times the square root of 5. Negative 6 times the square root of 5. The square root doesn't change, right? How come? Think about this with variables. This would be really simple with variables. What if I had, what was that again? What if I had negative 8x plus 2x? What's your answer? Yeah. We don't get like negative 6x squared or something crazy like that, right? How come? Because we're just adding up the numbers of x's. That's what a coefficient means. If the coefficient of x is negative 8x, that just means I have negative 8 x's plus 2 x's is how many x's? Negative 6 x's. Well, the same thing is true in this case. I've got a coefficient out in front of each of these radicals, and notice that the radicals are the same. Because those are like radicals, they're exactly the same kinds of radicals. What needs to happen for two radicals to be like radicals? Two things have to be the same. What are they? The same type of root, right? So they both have to be, they have to have the same index. They both have to be square roots in this case. And what else has to be the same?
Same number.
Yeah, the same radicand. The number inside has to be the same. If both of those are true, we have the same kind of root with the same radicands, then those are like roots, and we can add them up or subtract them, right? I've got negative 8 of those square roots plus 2 of those square roots is how many total? Negative 6 of those types of square roots, which are square roots of 5. Okay, give me thumbs on that part. Does that make sense? Okay, so we know there's part of our answer. Minus 6 times the square root of 5. And the other ones are easy. 16 plus negative 5 is 11. So there's our answer.
So order-wise, do we put the square root first? Or
It doesn't matter.
okay.
Doesn't make any difference. Okay, good? This one. Okay. Remember, I can only combine like radicals. For a radical to be a like radical, for these terms to be like radicals, what has to be true about the radicals? Two things. Have to be the, say it again? Same, okay, so the same kind of radical. Oh, no, the same, you're talking about the same radicand. You have to have the same number inside. What else? Well, no, not necessarily. The same kind of radical, right? They both have to be, like I couldn't add cube roots and square roots. They wouldn't combine, right? So they have to be the same kinds of roots, and they have to have the same radicand. So they have to be the same kind of, the radical has to look identical in each term to be able to add them up. None of those look the same, do they? So I can't add them, right? But maybe I could. What could I do to just go further and maybe see if some of them could eventually add together? Simplify them, absolutely. So if we were to make a factor tree out of 27, now that's a small enough number. Let's see if we can do this without even writing the factor tree down. What would that factor tree be? 3 and 9, and what would the 9 break up into? Okay, so 9, we could break this up into the square root of 3 times 9, right? And the square root of 9 would become an outside 3. Everybody get that? So when we're doing our factor tree for this one, Your goal is to see if you can turn one of those branches of the tree into a perfect square. So it's going to automatically turn into a couple, right? Well, what is a perfect square factor of 27 is 9. 9 times what? Times 3. And that 9 breaks up great into a couple of 3s. So I get an outside 3 and an inside 3, right? Okay? Okay, so the first one becomes, I got an outside 3 and an inside 3. How about the next one? Square root of 18. 9 and 2. So in that case, I'm going to get what outside number? Okay, good. The 9 breaks again up into a couple of 3s, so I know I'm going to get an outside 3 and an inside 2 this time. So we're going to end up getting minus outside number 3, inside number 2, and then finally, what about that last guy, 75? 25 and 3, I could break up 75 into 25 and 3, and what's the square root of 25? Okay, so I get an outside 5 and an inside 3. Well, if we simplify those, what's 6 times 3 times the square root of 3? 18 times the square root of 3. Minus 2 times 3 times the square root of 2. Okay, good. 2 times 3 is 6. I get an outside number 6, inside number 2. And then this guy's already simplified. Plus 5, radical 3. Are any of those like radicals? Yeah, look at those. These are like radicals, aren't they? We have the same kinds of radicals. I have 18 of those plus 5 of those is how many of those square roots of 3? 23. And then this guy was an oddball. The square root of 2 didn't have any, that one we're stuck with, right? Doesn't combine with anything. So that's my answer. Okay? I think that's a good place to stop. Aren't we out of here in like a minute? Okay. All right, we'll pick this up. We've got, a few more to do tomorrow, and then you can have a little extra time to review.